Please welcome a fellow Our Lady, Omayma Saeed.
All right, so hi everybody. I'm glad to be here today because it's my first RStats event in Africa. I'm a data scientist and I flew from Egypt. And surprisingly, I've met people before who weren't sure that Egypt belonged to Africa, but I believe people here know that or assume that. So we belong to the same continent. And I have an electrical engineering background, then I moved to the data science world, and in all my works and studies, I've always had a curiosity to ask about how things work, and specifically why not, and what if. And I took this with me when I moved to the data science world, so I would ask why a model works, why not use another model, or what if we change something about the model input, method, and so on. And this could be annoying to some people sometimes if they want to move forward and run without questioning their assumptions or how things work. But before talking about how models work or why they give a certain input or how to interpret their outputs, let's play a game with your mental model first. So each one of you has mental models, and our minds have complex models for sure that are very accurate, and scientists were inspired by them. But let's play something very basic. So each one of you will be a classifier, and I will show you an image, and you would label it with one of two labels. So the first two labels would be cat or dog, which are very well known in the image classification tasks. So if you think the image is more likely to be a dog, you will raise your hand, otherwise you will stay the same. Okay, so this is a trial, and then we will try another couple of labels. Ready? Okay. So here's the first photo. Okay, good. Second. Okay, so this was a simple one, and let's play with something else with an illustration that would change over time. And you're free to change your prediction according to what your mind tells you at any moment. And the new ones are duck and rabbit. Okay, so it will change, and you can change your prediction as well. Here we go. Okay, so I saw that some people stuck to one thing. They couldn't unsee what they saw, and others changed their prediction according to the orientation. But the most important question is why? Why would you give this label if you look to something? And scientists used to study how humans perceive things or see things, and sometimes they argued whether they see it holistically or analytically. But probably if each one of you give a different explanation for such a labeling task, I would hardly find someone who would give a quantified explanation. So probably nobody would say, this is a duck because the distance between these specific 2 points is within a certain range, and so on. And actually this example was inspired by example shared by Max Wolf online, where he fed this data to Google Vision API, and this is a video, so it should work. But, yeah, so what he did that he fed the same image with different orientation to Google Image API, and it gave different outputs at different orientation. And I just wanted to show you and see how it compares to what your mind told you. But whether it's your brain models or machine learning models, there is always a trade-off that when you go with higher complexity, you have this trade-off between complexity and interpretability. Okay, so there is always this trade-off between complexity and interpretability. And usually when you have more complex models, whether there are starting from random forests, which are not directly interpretable, to other things like deep learning, they could give you better results, better accuracy, but you will have lower interpretability. So you wouldn't get like a numeric explanation of why a decision was taken, why you predicted a certain value, and so on. And it might not be a big issue if you're just looking at cats and dogs or making simple decisions or with simple products that are not affecting humans' lives every day. But now we're seeing more adoption of machine learning and deep learning, and probably every company is labeling its products as AI-powered or machine learning enabled. Even if they are using like simple models sometimes, but they like to show how they are adopting the new trends and going with the deep learning models and so on. And the important issue is whenever this is affecting humans, we need to understand and raise the question of why all the time. And this is for several motivations and reasons. So for instance, last year we read that, or in the previous years, we read lots of examples about the use of machine learning to make decisions about humans or to affect their lives in healthcare, education, justice, and so on. For instance, there was an extended report about the use cases of algorithms in healthcare in the US, and it was covered in The Verge. And they didn't just speak about the algorithm themselves, they also featured humans who were impacted by such decisions. One of these humans was someone who suffered from cerebral palsy, and she used to have around 50 hours of home care per week because she had a human assessor who gave her that assessment. But once the decision was shifted to algorithms, there was a cut in her hours to almost 30 per week. And she was frustrated. She questioned this decision, and she had one question in mind: why? She couldn't find out why. But it was not only her, because also in Idaho there were similar cases where people appealed to understand why they are impacted by such decisions, but the state just said it's trade secret. And I'm not sure whether they were using a simple model or a complex model, but it's type of behavior where people shift the responsibility to the algorithms and say, it's not me, it's the algorithm, and you cannot question it, and we cannot reveal it because it's proprietary. And this is less transparency, which makes it harder to gain the social acceptance, trust, and be accountable for our actions when we have a certain product or decision as a company or developer. But there are also other stuff like justice, recidivism scores, or predictive policing that we heard about. And one of them, like last year, was reported on The Intercept about Taser or Axon Now that had police body cameras, and they claimed that they have tons of videos, and they were able to anticipate criminal activity from these videos and footages, and that their deep learning models would be able to differentiate between a jogger and someone who is fleeing a crime scene. And this was an engineer who said that, but officially Axon said, no, we're not taking any decision, we're not making automated suspicious product or something like that. All what we're doing is automated redaction, transcription, and reporting to help the officers be more efficient. But if they have all these data and probably they think about using all the footages, it could be possible to do more. And we can ask what else or what more you can do. And even in their videos online, I saw that in one of their demos entitled I'm in to connect and serve, they demoed an officer who got a signal from their system where capturing someone who is running to give them a warning that he might be going to steal a car. So in this case, you might think, okay, what are all the biases that the officers can inject? What is their point of view? How would they label the data in the first place? And so on. So this is the part of the ethical implications of our work and how we are impacting humans. And sometimes there are applications that should not be there in the first place if they are impacting humans negatively. But these are like large-scale products that could be available for government or like big entities. But there are other products that we deal with every day, and we know that we're impacted with, which include recommender systems, scoring, ranking, in search, or stuff like that. And some of which are like job recommendation or education matching when you apply to something. And last year there was a lot of articles about Amazon throwing away an AI recruiting tool that showed bias against women. And in the article they wrote that Amazon system told itself that male candidates were preferable. And even if you are a man who has the word woman in your CV, you might get a negative point or something. And I can understand how could this happen, because I worked in similar area and I could see how people could inject their biases or get so overconfident with their models. But I have also a problem with this narrative that we say Amazon system taught itself, or the algorithm cut your healthcare plan or something, because we who teach these systems, and they just learn from us. And we are the ones who design us. So this is part of throwing out the responsibility. And it's always human who collect and label data, write algorithms, and define metrics. And in each of these steps, something can go wrong, or something we can question all the time. So for instance, while collecting and labeling data, there could be bias in representation, distribution of the underlying data, or even the labels people put according to their perspectives and how they think and view the world. And while writing algorithms, there could be issues with the train-test split, or using features as proxies to something that shouldn't affect the decision, such as color, race, and religion. So sometimes people say we're not using these features, but they have a proxy for them. And another issue is the black box models, which we'll focus on today. And they are more about, sometimes you say, okay, we have higher accuracy, let's work with it without any consideration to anything else. And while defining metrics, sometimes people do not ask, what are we optimizing for really? Are we optimizing for a high-level business metric like engagement or time on site or click-through rate, without thinking about other impacts? And what is the impact of different error rates on different groups? So sometimes the error rate in general is okay, but it's higher for a certain group, so it could be higher for women or for a certain race and so on. So these are things to question, look at, and consider. Because practitioners consistently overestimate their model's accuracy, propagate feedback loops, and fail to notice data leak, as the authors of the paper, Why Should I Trust You?, argued. And this happens all the time, and if you're in a business context or a meeting with different specializations, you can see that whenever someone has a good model, sometimes they would run with it without questioning how and why it works. And that's why we have several reasons that we can sum up about why to have interpretable machine learning or care about it. On top of them are the ethical implications. So as we said, we wouldn't harm others or cause a negative impact if we ask all the time why and how things work. And the other thing is transparency. To be able to answer the questions of people, as the lady asked why I got impacted, for example. So to gain their trust and know that we are serving them if you are a company or a government or anything, not just serving the business objectives. And also sometimes this is a regulatory prerequisite in some countries that you should provide an explanation, especially in highly regulated industries like insurance, and similar industries. Another thing that's sometimes overlooked is debugging models. And this is from a developer or algorithm developer point of view, that if you have something to tell you why your model is good or bad or why it's doing this or that, you will have the ability to improve it and make it better and fix it. So this is even for the developer himself or herself. Another thing is security, and it became to attention later that there could be adversarial attacks. So if you don't know why you are getting a certain output and trust your model blindly, someone could change something in the pipeline, in the data, on how it works, and you would get a disaster at the end because it would totally change the decisions made by your model. And imagine this in case of self-driving cars or something that is really crucial. If someone mess up with your model and its output, and you're not sure how and why this works. And as we're now convinced that it's something important and something we would like to consider when we are working on models, we should ask, okay, how we should do this? But the good thing is researchers in the previous years started to focus more on building tools and frameworks for interpretability and producing explanations. And I would focus on two today. The first is LIME, which stands for Local Interpretable, Model Agnostic Explanations. And it's available now in two R packages, LIME by Tom Pedersen and IML by Christoph Molnar. And I would focus today on LIME in specific, but they are both giving the same or implementing the same concept. So the promise of LIME that it would explain individual predictions of black box models using a local interpretable model. So what does that mean? We are explaining a model using another model. And how does it work? It works for tabular data and images and text as well. And we'll see some examples on each one of these. So for tabular data in specific, what you do is you usually have a point and you have a prediction coming out of your black box model. So you would specify this point and say, okay, this is the point I would like to understand the result or the prediction for. So you specify it, and then you sample data from a distribution around it, and then you weigh these points according to their proximity to this point. And finally, you train a local interpretable model that is using the weights and the points you already sampled. And having all this, you can start to explain the black box model prediction using the local model. And this might be confusing at the beginning, but this is a good example in Christoph Molnar's book. And I put together a Shiny app also to show you how is it local and how each point could differ, what are the weights that are given to the points around it, and how the model is local for each point. But let's see an example with a bit of R code. So we're going to use a data set which is very well known. So any guesses? Yeah, right. So for research purposes, anybody here haven't heard about Iris? Okay, that's good. It's a chance that you know about it, because chances are you will find it somewhere on your way later, whether using R or Python or any other languages. So basically, we know that Iris, we go for a classification task to check the three species of Iris. And if we have a black box model, here we should think about anything. We'll try random forests. And then we would like to explain the results of a random forest that we trained on a new instance. So what we are going to do is to create an explainer using LIME. We pass the trained data and the model. Then we create an explanation for a new instance. So here we say, let's explain the prediction for this particular instance using a local model. And we define the complexity of this model by saying that number of features are 4. So we say use all the features we have to train a local model and explain the prediction of the black box model. And having all this, you will have your data in a tabular format, or you can plot it easily using plot features function in LIME. And what you get here is an illustration of what supports this prediction or contradicts this prediction according to the local model. So we can read this as the petal width between this range supports the prediction of setosa according to the local model, while the petal length between this range contradicts the prediction of setosa as per the local model. And to emphasize that it's local model, if you look to two setosa explanations side by side, you can see that they have different values. So you cannot take one of these values and generalize on everything and say they are not rules. So you don't say if it's under this value, all the points would be setosa. No, it's just local for this specific point. And you can plot other instances around and see that each one had unique and different values. And similarly for images, and this is the image you saw at the beginning. So the prediction by Keras model was a certain type or species of dogs. And I wanted to explain this using LIME. So what we do is LIME basically segments the photo into small areas, and it makes changes and perturbations to see whether it's affecting the final results or not. So it basically asks what are the most influential pixels or features in this image. And then you can plot your explanation. So you would say, okay, please plot the explanation for this according to the local model, why you got a toy terrier, and it would just highlight the pixels that are supporting this explanation according to the model. And in this case, it makes sense because it's a good example. Sometimes it doesn't, but it depends on the photo and the number of pixels you segment to and other variables that you can play with. And because sometimes there could be smaller objects in your image that are located in smaller segments of this image, you have a variable of superpixels that you can increase the resolution, and you say, okay, go for 50 or 100 or 150 superpixels, and it will segment it to smaller areas, perturb them, and give you an explanation according to them. And similarly for the cat you saw, it was classified as tabby cat or Egyptian cat. These were the higher two labels. So you can also plot side by side the explanation for several labels if it's a multi-label classification task. But not only can you plot what supports your prediction, you can also plot what contradicts, and here it's the red areas which are visible to be away from the cat itself. So this is good to show us, okay, what supports our prediction, but as we said, there is a good benefit we get when we debug our models. And there is a good example in the LIME paper, or Why Should I Trust You paper, that they have Husky classified as wolf. And you might look at it and say, okay, maybe there are some features in this specific Husky that made the model think it was a wolf. But when they plotted their explanation, they showed that it was the snow in the image that supported their explanation, or the white area in the background. And they knew why, because all the images they fed to the model, including wolves, had snow in the background. So here it gives you more insights about your model. It's not your model that is very bad, it's about the underlying data. So in such case, if you are in a practical situation, you would go back, recreate your training data, improve it, and test it. And similarly for text, I had the famous IMDb review sentiment classification task, where you have classification from IMDb website, and you would classify it as positive sentiment or negative sentiment. I used a Keras model. This was the black box model, and then I used LIME to create an explanation. And with a new review, starting with this documentary was boring and quite stupid till the end of the review. And this shiny application is available inside Lime package, so you can launch it whenever you have a text explainer. And in such case, it showed you that boring, stupid, dumb, and waste supported your explanation, while information contradicted it, which is neutral or is not essential to this example in specific. And you can play with different parameters to say, give me the most, the highest 10 or 5 or any number of features to explain your model with. So with all these examples, we can see that Lime provides a human-friendly explanations, and it gives a fidelity measure. So for each explanation, it would tell you the explanation fit, and that means how reliable is this local model or this explanation. Because it's not 100% explanation that you would take and say, this is it, or that's what's affecting our models exactly. And something else is it can use other features than the black box. So in your black box model, you can have a transformation for your text into embedding vectors, or you can, in your deep learning model, you can have your features transformed into other representations. But at the end, it will give you the explanation in the original features you fed, in terms of words, pixels, or features you fed in your tabular data. On the other hand, it has some shortcomings, like the definition of proximity that is not well defined or resolved, and researchers try to play with some parameters and experiment with it. And sometimes it has unstable explanations when you have 2 points close to each other and they have totally different explanations. So these are stuff that are still under research, but after all, it gives you a good start to say this is something we can debug our models with or understand our models better with. The second thing is Shapley values, and Shapley values also implemented in the IML package. And it has a different philosophy than Lime, so its promise is to explain the difference between the actual prediction and the average prediction of the black box model. And it's inspired by the game theory, and as it thinks about the features as players in a game, and there is a payout, which is this difference, which you would like to explain or distribute on them. So we can see an example on a regression task using the bike sharing data, where the task is to predict the number of rides on a certain day, given the temperature, the weather data, and other features on this day. And as usual, we train and explain. So first of all, we train a black box model, and here I also trained a random forest model. And then what you do is to create a predictor using the model and the trained data, and you need to have access to the trained data while using Shapley values. For Lime, you can have just the model, the Keras model or something to deal with, but not necessarily the whole trained data. But in Shapley values, you need all the trained data to be accessible to you, because it does some operations using the training data under the hood. And then you can calculate the Shapley values using, for a new instance, using the predictor you created. And what you would get or you would plot is something like this. So you have the actual prediction, the average prediction, and a difference between both. And what you're explaining is the difference between them. So what you can read here, you can say the contribution of the temperature value 4.4 to the difference between the actual prediction and the mean prediction is the estimated Shapley values, which is around negative 1,000. On the other hand, the wind speed 8 has a positive contribution to these difference. And it's also local. So if you have two different instances, they will have different explanations, because you consider this as a game. Each one is a new game where all these players play, and there is a result which is the difference between the actual prediction and the average prediction. So it's not something that you would take also and generalize or use across different instances. And also, so it's always said that Shapley values has a solid theory, because, a mathematical background, and it's applied in other domains. And it looks at the fair distribution of these payout between all the players. And on the other hand, it's computationally expensive. So the computation time increases exponentially with the number of players, because you form coalitions from all the possible combinations of the features. And it can be misinterpreted because it's not intuitive, or you don't take it to someone who is not familiar with it and get it in at first glance or something. And also, if you are picky and want to explain your stuff in terms of 2 features or 4 features, or defining a certain complexity of the model, it wouldn't be the ideal way, because it prefers to use all the features. So there are other methods. It's not only Lime and Shapley values. There are anchors, and there is a paper about it as well. And there are more stuff out there to help us gain better understanding of our models. And for the packages in R, there is Lime, IML, and there is also Dalix that has been there for a couple of years. And it has good also documentation and examples online. And some of the good readings you could read in such topics, a booklet about the introduction to machine learning interpretability. It's a general thing with some explanation of these methods. And if you're interested in the ethics point, there is also a nice small booklet about ethics in data science. But if you want to get into details about how Shapley values are implemented, or how Lime is implemented, there is recently the interpretable machine learning model by Christophe Molnar. It's available online, and it has all the code available, plus the Lime package itself. And I believe, like, Christophe Molnar himself was talking that many researchers who work in this area sometimes get disappointed because people tell them it's not worth it, or it's not good enough, or things are, reality is different. But as I said, many practitioners really don't go for machine learning in highly regulated areas or in other areas, because there is no explanation of what they are doing. I would argue that there are also many who don't care and just create what they want to create, getting fascinated by the technology, the new algorithms, without questioning things, without asking why not, and what if. But I think we are in the position to ask this, and we have to care enough, because who else would care? And it's not just about data scientists or algorithms developers. It should be on the table, even if you are a business person or a product manager or anything. Someone has to bring this up and say why we're picking this. Are we having a negative impact or not? Because it's our responsibility, and hopefully there are more people who care to question things and use tools and have them in their pipelines with more packages and tools available in the market. Thank you.